B2.
All right, so welcome to the University of Texas at Austin's class on real-time digital signal processing for the spring 2014 semester. So this is the revised schedule of what we've done, and so today we'll do lecture 6, part 2 on infinite impulse response filters. There's a handout, or sorry, there's an appendix O in the course reader to be aware of on all past filters that will come up today. It's appendix O. Okay, so again, lecture 6, part 1. And any questions from, sorry, lecture 6, part 2, sorry, for today. Any questions from previous lectures? So last time we talked about the many roles for filters, and we talked about the Biquad, and the Biquad is a basic building block for implementing infinite impulse response filters. This is true for both parallel and cascaded implementation. In lab, you'll do a cascaded implementation. That is to say, several biquads in cascade in sequential order. So today we'll talk about direct form. We'll also talk about frequency responses and how they relate to pole and zero locations. So we've done all this. All right, so let's get started where we left off, lecture slide 6-7. So we finished up last time on the biquad. The biquad was 2 poles and 2 zeros. And this is, so we can start there. So for the biquad, we have 2 poles, P0 and P1. And we have 2 zeros, Z0 and Z1. And we can write the biquad in a factored form, as I show here, using positive powers of Z. So it's the same as we had before, it's just factored. And you could write out this transfer function, and this is a very important representation of a filter. We can represent it in what's known as pole zeros in gain form, or PZK. This is one of many standard formats. So I have a list of pole locations, P0 and P1. I have a list of zero locations, Z0 and Z1, or in MATLAB, these are vectors. And then finally, I have a gain term, which is C. Okay, so I have some degrees of freedom here in designing the pole and zero locations to obtain a certain frequency response. We'll talk about how to do that today. So this gain term is also another degree of freedom. We can scale by choosing C the magnitude response. It doesn't change the shape, but it changes maybe the peak value changes. So we'll scale by capital C in absolute value. All right, so if we go ahead and factor out go ahead and push through the terms here, we get in the denominator, we get, Z squared, what else we get? Minus P0 plus P1 times Z to the minus 1, sorry, times Z, plus P0 P1. Okay, that's your denominator. The numerator, the C can be carried through if we want. And you'll see the connection back to B0 and B1, B2 in the previous slide. So here we kind of filter or multiply through. So instead of Z squared, I now have CZ squared. And I have C times Z0 plus Z1 times Z, and finally C, Z0, and Z1. Okay, so this, I've gone from factored form in this pole zero gain representation, and I've factored out the factors to get the unfactored form, which is now more familiar. This is what we'd seen previously, although now I can divide through by Z squared, and I can get what was familiar in the last slide, which is B0, B1, B2, and so forth. So in the last slide, which we did in part 1, right, this was our transfer function. So I have 3 feed-forward coefficients, B0, B1, B2. This is the FIR part. I have 2 feedback coefficients, A1 and A2. That's the all-pole part, the left-hand side of this biquad. All right, so again, we really end up with several degrees of freedom. So now we can go to a frequency response. This is fine in the Z domain, provided the poles are inside the unit circle, and that's the way we've defined filters, that they're bounded input, bounded output stable. So again, assuming the poles are inside the unit circle, we can make this change, right? Z equals e to the j omega, so that we can convert the transfer function to a frequency response, take the magnitude of that to get the magnitude response. And a few things about magnitudes, right? If I take the magnitude of A times B, right, this is the magnitude of A times the magnitude of B. So if I have a magnitude, and the same thing if it's A over B, if I have magnitude of A divided by B, it's the magnitude of A divided by the magnitude of B. So I can take all these terms, I now have 5 terms in here, and I can simplify this absolute value of products and divisions to be the products and divisions of the absolute values. So I get the product here becomes the product of 3 absolute values, and then in the denominator the same thing happens. I get 2 more absolute value terms. Now these become significant in mapping or understanding the frequency response in terms of selectivity. Is it low pass, high pass, band pass, etc.? And the reason for that is that each of these distances, so if I have A and B are complex numbers, the absolute value is just Euclidean distance between them. Good old stuff from high school. Now, what's important for us is that now what's interesting is that the 2 complex numbers have significance for us in terms of frequencies. We have the one term e to the j omega, which is where I am on the unit circle, and omega is my frequency in radians per sample, and p naught is the distance, p naught is the pole location, and so the distance between where I am on the unit circle and the pole location influences dramatically the magnitude response. If this distance is really small, that is to say the pole is really close to the unit circle, this distance that's very small, since it's in the denominator, means that it has a very large increase in the magnitude response as a result. Now, in the other way, the numerator terms directly multiply the magnitude response. So if my 0, for example, is on the unit circle at angle omega, then this distance is 0. And I have now zeroed out the magnitude response at that frequency value. We'll have lots of demos of this coming up. So the pole and 0 locations matter a lot. And when the poles and zeros are separated at an angle, we can come up with some very simple rules of thumb, and we'll see them play out in homework, and we'll play out in demos today. Poles that are near the unit circle, remember, the poles can't be on the unit circle. And why is that? What's the problem? It's Bibo unstable. Now, if we want a Bibo unstable LTI system, then yes, poles on a unit circle are wonderful. That's how we can generate sinusoids and other oscillating signals. So they have excellent uses. For us, though, we're doing filters here. We don't want to generate any new frequencies. Sorry, we want to pass and reject certain frequencies. We don't want to have an oscillator usually in our filter. So 2 different things. So the poles that are near the unit circle indicate the pass band. So as I say, the angle, remember in the z-plane, is the angle with the positive real axis that tells us frequency content. So the poles that are near the unit circle indicate the filter pass bands at the angle of the pole, and zeros that are on or near the unit circle indicate the stop bands. Now this is only true when they're separated at an angle. If they get too close to each other, they get some interactions that are pretty interesting. But as long as they're separated here, we can make these claims. So let's see a couple examples of that just on the slides, and then we'll do some demos at the end of lecture. Okay, so again, our transfer function for the biquad: 2 poles, 2 zeros, and a gain term, capital C, which is in general complex. And again, we can write this either with positive powers of z or with negative powers of z. It doesn't, they're the same. Okay, so again, 2 poles, 2 zeros, and a gain. Again, just for notation, we'll represent poles with an X and the zeros with a 0 or an O. And I mentioned earlier that our coefficients B0, B1, B2, and A1, A2 are going to be real valued because the input signal is real valued and the output signal is real valued. There are some cases when the poles and zeros might be complex valued that are not conjugate symmetric, and they could lead to complex coefficients. We do use this. We'll have one example later in the class. But other than that one example, the more typical case for real valued input signal is to have real coefficients. This means that the poles are going to be either conjugate symmetric, that is to say they'll be in the form, A plus or alpha plus or minus J beta, and A plus or minus, right? So there'll be A plus JB, and so alpha plus J beta, and alpha minus J beta. Or they're real valued, as we had seen in Lecture 6, Part 1. Zeros are going to have the same structure. They'll be conjugate symmetric or real valued. So now I'm giving you a couple of examples, and the first filter follows what follows what we had in the previous slide. I've got poles separated at an angle. So here's my angle, right? I have poles separated at an angle from the zeros, and this angle is my discrete time frequency for any point that's on the unit circle. Right? So this is my unit circle. This is z equals e to the j omega. That's my unit circle. I have two zeros on the unit circle, and I have two poles that are close to the unit circle but not on the unit circle. Right? So each of these poles have, this one's a little tricky, this first one. It gets trickier going to the right. So this one has a very small angle with respect to the positive real axis. Okay, so think about what selectivity this filter on the far left has. Is it low pass, band pass, high pass, band stop, all pass, or notch? Okay, so in this case, the poles again tell me that I'm going to pass frequencies at the angle of the poles. And why is that? Because if I evaluate the frequency right there, the distance to the pole is very small at that frequency. In fact, it's the smallest distance possible of all the possible frequencies on the unit circle. This distance is so small, and 1 over that distance is something very large. So the magnitude is very large at that frequency. And the same thing happens at this frequency, the frequency of the other pole location. That distance is also very small. If we look at the DC response, which is right here, when z equals 1, right, so this is z equals 1, which means omega equals 0. This is 0 frequency. That's getting worse. There we go. Omega equals 0. And if you look at this, I have a small distance from z equals 1 to the pole location and a small distance from z equals 1 to the other pole location. And those are both very small distances. They're in the denominator, so I'm going to get a very large magnitude even at DC, if these poles are really close to z equals 1. Now, if I look at higher frequencies, go all the way to pi and minus pi, I'm now close to the zeros. So I look at frequency pi or minus pi, trying to get on the unit circle there. There we go. So at z equals minus 1, so when z is minus 1, this is the highest frequency possible. This is omega equals pi. It's also omega equals minus pi, and 3 pi, and minus 3 pi, and so forth. All right. So this is the highest frequency possible in discrete time. Corresponds to what frequency in hertz? Something over 2? It is something over 2? What was it over 2? Half the sampling rate. Right? So this corresponds to half the sampling rate. Highest possible frequency in hertz that we can capture from sampling, if we were thinking about this in continuous time frequencies. All right, so back to discrete time frequency. So I have an angle of pi or minus pi to get me here. And if I look at the distance to the 0, it's very small. And the distance to the other 0 is very small. So the magnitude response will be very small at omega equals pi. Also, if I look at the magnitude response at the same angle as the 0 is located at, I have a 0 in the magnitude response at that angle. Because the distance between the point on the unit circle and the 0, which is on the unit circle, is 0. They coincide to the same point. They coincide at the same point. And my magnitude response goes to 0 whenever I have a 0 of the transfer function on the unit circle. There's a connection. So now what kind of selectivity do I have on this leftmost choice? It's low pass, right? So I'm passing high frequencies and rejecting a couple. So I'm passing low frequencies, rejecting a couple of high frequencies, but otherwise have very low magnitude response. And we'll see demos of this shortly. Okay. All right, so that's interesting enough. So that's now. What if I switch the order? What if I put the poles over close to pi, where z equals -1, but not on the unit circle? And I put the zeros over here close to z equals 1 and on the unit circle. What would that filter be in selectivity? It would be high pass. Okay. Let's think about another one while we're at it. Let's try. All right, so let's go. I'll draw that last one. So again, I take a. So if I put my poles over here, sorry, I want my poles over here, wrong place. So poles are over here, close to z equals -1. Zeros are here, close to z equals 1. That would be a high pass. And this would be low pass. I can do one more if I put the poles here. What kind of filter would that be in terms of selectivity? Bandpass. All right, so I'm passing frequencies at pi over 2 and minus pi over 2, and I'm rejecting frequencies at 0 and pi. So it'll be a bandpass filter. Last one, how about we put zeros at pi and minus pi and a pole at 0.9 and minus 0.9. Not a notch. Band stop, right? Band stop. So I'm passing low and high frequencies and I'm attenuating mid frequencies. So it's band stop. So again, this second one up here is band pass. And this one is band stop. All right, now it's getting more interesting. Now the poles and zeros are at the same angle. Now something else is going to happen. Something kind of unusual. So you can reuse your answer in just a second. Okay, it's coming. All right, so this middle one's interesting because if we apply this geometric argument, I know that at this angle, so again, we're at the middle one here. So in the middle choice, if I look at the frequency content at the same angle as the 0, what's the magnitude response? 0 at that frequency. The pole can't alter that. But if you look at another point near it, the distance from the 0 and look at the distance to the pole, they're pretty similar. And if you look at this, again, the distance from the point to the 0 and the distance from the point on the unit circle to the pole, pretty similar ratio. In fact, it's a constant. As you go around, you'll pick up, outside of this small range of frequencies, the rest of the frequencies have a very similar ratio of the distance from the point on the unit circle to the 0 to the point on the unit circle to the pole. What kind of filter is that? Yeah, so notch. It's a notch filter. So in terms of magnitude response, so this is a notch. So in terms of magnitude of response of the notch filter, right, so this is a notch, and this is the magnitude of response. So there's your notch filter. And this notch frequency is what? What is this? Where's this? What frequency is being eliminated? It's the angle right here. So there's a mega naught. That's a mega naught. Now here it happens to be pi over 4. And so I'm not drawing this very well to scale because this goes all the way out to pi. Right? We plot the frequency response from minus pi to pi, or we can go 0 to pi. Here I want to go minus pi to pi just for, it's a little more, I think it's visible. It's a little more visible to see the notch in action. What's this left frequency that's being notched out? Negative omega naught. Right, so this is a way to remove a certain frequency. We do this with power line frequencies, 50 hertz, 60 hertz, depends on the country, or any other interference that's sinusoidal or periodic that's at a certain frequency. We can notch it out this way. So in homework 3.1, you're asked to filter a noise, a signal and noise, and you start with interference outside of the transmission band, and when you apply the filter, you'll get an increase in SNR because you'll attenuate the interference that's out of band. When you put the interference in the same band of frequencies as your signal, and you apply a bandpass filter, both noise and interference come through. But we can get rid of the interference on a subsequent stage of processing, which is to notch it out. And we do this in practice. So for noise and interference that's outside of a band of frequencies we care about, we apply the appropriate bandpass filter or low-pass filter, whatever it happens to be. And to get rid of interferers that are periodic inside our transmission band or band of interest, then we can do a notch filter. Okay, next one. I guess what's left, right? That's So by process of elimination, what's the last one here? It's all pass, right? So this last one's all pass. Let's figure out, and again, there's a handout, Appendix O, in the reader for this. So why is this last one all pass? Again, if you take any point on the unit circle, any point at all, and you have to have the right configuration. So the poles have radius r, and the zeros have radius 1 over r. If that's the case, then the ratio, again, from the 0 location to the point on the unit circle and the pole location to the point on the unit circle, that ratio remains constant all the way around, which is pretty interesting. And the Appendix O derives it. Now, so all these are nice diagrams. So how do I get filter coefficients from this? These are, great. I can design all kinds of, filters here with just putting poles and zeros down with different selectivities. Great. Let's not stop there. So how do I get back to my coefficients? Correct? Almost. I have one more degree of freedom. So if I know where my poles and zeros are, I know my transfer function up to this constant. All right, so now I have to pick, so how do I pick the constant? Is 0 a good choice? No, 0 is a terrible choice. Give me a good choice, a simple one. 1. 1 is a fine choice, okay? Now, we can be a little more careful about it and say, well, I can normalize the filter. So, for example, I could say, well, in the case of, let's see, in the case of the notch filter, in fact, in all three of these cases, I have a response at DC that is not 0. So what I can say is I'm going to choose C to make sure that the DC response is 1. Okay, so I can do that. It's just a matter of solving for C, basically, by plugging in Z equals 1, which is the DC response, and solving for C. It's one equation, one unknown. And okay. Now that I've done that, so and just in case you need to pick something fast, C equals 1. It's a good choice to start with. Now what do I do? What do I do next? So I have this, now what do I do? I'm not yet to coefficients. Still in poles and zeros and gain. What do I do? It's not meant to be difficult. Multiply out. That's it. That's all you do. Now you have a filter. Now you have a biquad. So once you know Z0, Z1, P0, P1, you multiply out those values, as we saw in the previous slide, to simply get your coefficients. All right, so I know that A1, this feedback coefficient, is the sum of the pole locations. Oh, yeah. And then the A2 here is the product of the pole locations. There you go. And then for the numerator, if C is 1, then the same thing happens. B0 is 1. B1 is the sum, negative of the sum of the zeros. And B2 is negative of the, so B2 is the product of the zeros. That's it. And you now have a biquad. So now you know the difference equation to implement the biquad for any input signal. Again, demos coming. Any questions on this? It's pretty important. So you don't have to run software to design your filter necessarily. Let's talk about a couple now. So again, the biquad's a building block, and so if I want to do a fourth order filter, I cascade 2 biquads. Put them in sequential order. One feeds the other. Okay, so if I have a fourth order filter, 4 poles, 4 zeros, I'll have 2 pairs of conjugate symmetric poles and 2 pairs of, or I'll have real poles, and so I have a pair. One, usually in filters, if it's fourth order, I'll have 2 pairs of conjugate symmetric poles. That's the more common case. But anyway, so I have 2 pole pairs. One goes to biquad 1, one goes to biquad 2. I have 2 zero pairs. One goes to biquad 1, one goes to biquad 2. So I can realize higher order filters with just cascading biquads. What about a third order filter? What do I do? Let me help you a little hint here. What do I do for a third order filter? Cascade a second order and a first order. How do I get a first order filter out of this? What's the second order? How do I reduce it to first order? Have a zero and a pole cancel each other out. That's one way to do it. That's one way to do it. But in terms of coefficients, what happens to the coefficients? The pole zero cancellation works. What happens to the coefficients? They go to 0. Which ones go to 0? A2 and B2. So if I let B2 be 0 and A2 be 0, this lowest branch goes away, and I'm left with a simple first order filter that has 1 pole, 1 zero. From the same filter structure, right? No problem. All right. All right, let's talk about, so that's the way we're going to implement it. In practice, if we go with really high order filters, 10th order IIR, 12th order IIR, we're better off with cascaded biquad. And if it's 9th order, then we'll have 4 biquads in a first order section. Okay, it's a lot more robust, and we'll talk why that is. We'll talk about it now, I guess. Let me go back to how we got our difference equation coefficients. And we got that by taking pole and zero locations and adding and multiplying them together. And if you look at that, it looks pretty harmless. It's like, okay, how bad, what is so bad about multiplying 2 numbers together? So you tell me what's bad about multiplying 2 numbers together. What happens? They're complex. That's okay. So if I multiply them together, in fact, they're conjugate symmetric. So I'll get a real answer out of this, which is nice. That's what I want. But what happens when I start multiplying two numbers together? What happens to the number of bits? Doubles, right? Okay, so let's say that P0's double precision and P1 is double precision, and I multiply them together, and I want to sort it back as double precision. How many bits do I lose of mantissa? How much accuracy do I lose? I'm half as accurate, which is a very safe answer. And how many bits would that be? How many bits have I just thrown away? How many bits of mantissa plus sine are in the double 64-bit float. IEEE format. 44? Do better than that. We can do 40. It's bigger than 44. It's bigger than 48. I know you. 50. Okay, if we include 52, if we include the sign, it's 53. 53 bits of mantis and 11 bits of exponent. And I know it's not a multiple of 2. We don't know why. All right. So it's an IEEE standard. I think from 85. It was in the late 80s. Okay, so whatever. They were thinking something else. So 53 bits of mantissa plus sign, 11 bits of exponent. And so if I multiply these two together, I've just thrown away 53 bits of accuracy, which is how many digits? Roughly 8 bits a digit, 6 digits of accuracy just got thrown away. Doesn't sound like much. And for a biquad, it's not that big of a deal. But if I were to, in some cases, in fact, in many cases, if I do the unfactoring by just multiplying through the poles and zeros, and if I then refactor back to poles and zeros, the pole and zero locations change because I've thrown away bits, thrown away information. And the poles and zeros can move around. Now, is that a problem for zeros if they move around? Probably not. A little change in the magnitude response, maybe. Doesn't affect bibo stability. But if the pole locations decide to move around, why is that bad? It can change the bibo stability, and this is exactly what happens in practice. So what we like to do is to limit the amount of expansion that we do from the factored form to the unfactored form, and we control that in the biquad. Here we just have one expansion. If we do this going from factored to unfactored form for, say, a third order system, this last term is P naught P1 times P2. 3 terms multiply together, and I throw away now 53 bits and 53 more bits. If I go to 10th order, which you'll do on homework, or close, you could be on 10th order in homework, I now have 10 poles multiplying together for this last term. I've now thrown out 9 times 53 bits. Thrown out a tremendous amount of information. Okay, so the higher the order, the more perturbations possible when you do this expansion. So what we try to do in practice is limit, by using biquads and cascading biquads, to limit the expansion of poles and zeros into this unfactored coefficient form with feedback and feed-forward coefficients. This is why we have more than 20 different IIR filter structures out there. All right, so let's do a little bit of realizing higher order filters but using direct form. This will be in the lab this week, I think. And then next week we'll do cascaded biquads. Okay, so this is the direct form, which works pretty well for low order filters and has numerical issues for the reasons I described earlier for higher order filters. All right, so this is a direct form IIR realization. So IIR filters have a rational transfer function, that is to say it's a ratio of 2 polynomials in this case, non-negative powers of z. We can always multiply through the right power of z to make these positive or non-negative values of exponents in z. But we'll go with the negative here. Again, this relates to implementation. Each z to the minus 1 is a delay. All right, so if I look at this and work backwards like I did many slides ago, where I give you the transfer function, I want to work backwards to the difference equation. And I can do the following. I can multiply, so I can multiply left and right-hand sides by the denominator, and then multiply left and right-hand sides by capital X of z. And that's all that's shown here. So this term in front of capital Y of z is just a compact representation of the denominator. And this summation is just a compact representation of the numerator, right? This is the FIR section in front of X of z, capital A line. And this is the feedback portion multiplying capital Y of z. All right. Now I can take the inverse Z transform. So this one looks a little complicated, but if I just look at one term at a time, it's b of k, which is a constant for a given k, times z of minus k times x of z. The inverse transform, x of z becomes x of n, z of the minus k becomes a delay by k samples, and then the coefficient b of k comes out front. It's just a constant. Doesn't depend on discrete time index n. So that's my right-hand side. Left-hand side, the one term simply becomes y of z, and that comes down here. That's the one term. I then add to the right-hand side this summation. And so what is the inverse Z transform here? Well, again, this term is being multiplied by a capital Y of Z. So A sub m is a constant with respect to little n, the discrete time index. Z to the minus m means I delay by little m. And then finally, the inverse Z transform of capital Y of Z is little y of n. So that's my term on the left. Corresponds to the inverse Z transform of this summation times capital Y of Z. So I have two summation terms, and it should look pretty familiar now because the term on the far right here is just the FIR filter applied to the input signal x of n, and nothing more than that. Just a tap delay line applied to the input signal. And I have capital N delay elements. Left-hand side, a little more involved, but this is nothing but feedback. I'm working with still a tap delay line in its own way. It involves current and it involves only previous values of the output, which makes sense because I'm trying to compute the current output value. I don't know what that is yet. So I'm going to compute the current output value based on previous output values and the current and previous input values. Okay, so again, back to this term, this left term here. This is a tap delay line, and I'm just storing the previous output, the output 2 samples ago, all the way up to the output capital M samples ago. It's just a tap delay line applied to the previous output samples and nothing more. And so I pick off the right delayed value and I scale by the appropriate feedback coefficient, A sub m. In C code, it's just 2 for loops. Multiply, add, multiply, add, multiply, add. So it's the same code that the reason direct form is so popular, you can take the code that you've written for the FIR filter, which is the right-hand term, and reuse it, and then adapt it for the left-hand term, the left summation. It's the same code, but you start with the previous output value, y of n minus 1, instead of the current input value, x of n, sorry. So here it's tap delay line, x of n minus 1, x of n minus 2. The left-hand term is a delay line, y of n minus 1, y of n minus 2, and so forth. So it's just 2 for loops, down counting, multiply, add, and you add the two results together to get the final answer. So it's not too bad. Okay, let's look at the multiply involved, the arithmetic involved. I've got really 2 vector dot products happening here. I have a vector of feed forward coefficients times a vector of current and previous input values. I have another vector dot product, which is the previous output values and the feedback coefficients. So I end up with a total of m plus n plus 1 multiplication and addition operations or accumulate operations. I need to store the capital M previous outputs and the capital N previous inputs, and I need to store m plus n plus 1 coefficients. So I'm linear in terms of complexity in both in computation and in memory storage. So I'm linear in both. The coefficient is 1, so for as many previous outputs and inputs, the computation, as I say, as many coefficients as I have in the filter representation, I need exactly that many multiply accumulates. And for as many coefficients as I have in my filter, I need twice as many memory locations. I need to store the coefficients, and I need to store the previous inputs and outputs, and the current input too. Okay. So it's very much what you saw on homework 2.3 with the FIR filter case, which is the right-hand term. We just now extend that to include the left-hand term. It's just another set of coefficients. It's another set of multiply-add operations. Go ahead. The order is going to be the number of poles, and the order will be capital M. The order is the number of poles in an IIR filter. And for an FIR filter, it's the number of zeros. Let's look at the block diagram of this, and it should look really, really familiar from previous lectures. So this is the difference equation, which I show on the far right here. So here's our difference equation. I have, again, a tap delay line applied to the input, and that's here. So I have a tap delay line vertically instead of horizontally. I keep track of the previous input values, x of n minus 1, x of n minus 2, etc. I have another, so that's the left hand. So this is the first term, corresponds to the feed-forward section, the FIR section. The second term corresponds to the feedback section. The second term is a tap delay line, remembering the previous output values. Same structure, same code can be used for both. Makes it really easy to implement, very fast to implement. Whether it's in MATLAB or C or assembly or whatever. Okay, that's the good news. The bad news is, it's kind of sad news, no matter what I do, I cannot, well, there are some exceptions, but in general, no matter what I do, I lose LTI as soon as I implement, and there's really nothing I can do about it. Because in order to make this an LTI implementation, I have to maintain all the calculations in full precision. I can't throw away any bits. That is completely impractical. Because what happens in this feedback path is that the word size keeps increasing. Every output sample, this keeps, every time I multiply, I double the number of bits. I multiply again, I add another, 16 bits. So this for 16-bit values everywhere. The first time through, I need 32 bits. The next time through, I need 48, 64. It never ends if I'm not going to throw out any bits. So the bad news is when I implement, again, there are a few exceptions if I choose my coefficients just right. But generally speaking, I lose LTI here. I lose LTI. I'm going to skip this is another direct form. It's a direct form that actually leads to the biquad that we had before. It's the same kind of approach. Let me go on to the demos. So demos I'm going to have to do outside the browser. So I'll do a few of them. So start with the first one here. So let me run that back. Okay, this is a first order filter with one pole location and 1 0 location. And I'm going to move the pole and look at what happens in the Z domain, the discrete time domain. As to say, this is a transfer function, one pole location. There's the numerator, feed-forward coefficients, feedback coefficients. Impulse response, right? This is at 0.892, almost 0.9. Let's go to 0.9. Fine, 0.82, I guess. So this is 0.892 to the nth power. And you'll see that it has a low-pass magnitude response. I'm plotting from, this is really minus pi to pi. This is the frequency axis divided by 2 pi. And this is the phase, for what it's worth. So if we so right now this is a pole near the DC, or omega equals 0 frequency. It means I'm going to get a peak at omega equals 0, which is true. And as I go away from omega equals 0, the distance to the pole gets bigger and bigger. That is to say, the magnitude response gets smaller and smaller. Now I'm going to let the pole move from right to left, and you'll see that as the pole gets away from the unit circle, it has less and less effect on the magnitude response because the distance to DC now is increasing as I move the pole. Here it's almost canceling. The pole and zeros are almost at the same location, and I'm left with almost the identity system. The response is just an impulse. Now as I move closer to minus pi in frequency, which is over here, is equals minus 1, then I get more and more magnitude at pi and minus pi. And I get a high-pass filter. Right, so that's one pole moving around. And I'll just run it as a, or maybe not. Let's try it again. All right, so there you go. And if you'll notice that you get as the pole moves into negative real values, you'll see that the impulse response is just the pole location to the nth power times the step. So when the pole location here is at basically minus 0.519, this is minus 0.159, sorry, minus 0.519 to the nth power. So it's going to alternate 1 minus 1, 1 minus 1 in sign. All right, number 2. We're going to let the 0 move around. Okay, so initially it's pretty much at the z equals minus 1 or pi or minus pi frequency. So there's your 0 in the magnitude response. It corresponds to that angle of the 0 location. The pole is close to omega equals 0, so I get a peak at omega equals 0. I'll let the 0 move around. Okay, so if we let this roll, pause it right there. That is what kind of filter? Notch. Okay, so this is a first order notch filter. Or well, you could argue band stop. You could argue lots of things here. But I think the most accurate is notch. The best answer, I think, is a notch. Because you are eliminating one frequency, and otherwise you're trying to provide as close to an all-pass response as you can. Now, as the pole goes away from the 0, you'll notice that this response over the around 0 is not as sharp. So let that roll. So it's just not as sharp. In fact, if we, let's see, and we're back to what we had earlier. Same kind of configuration. So we're stopping 0 frequency and passing pi and minus pi.
I was just going to ask you, what if we add 2 more poles on the left side of that U circle? Would that increase the path band essentially?
Good question. So that is a very good question. So if we add, so now if we have 2 poles, you'll notice that right now it's not too interesting. It looks like a kind of wide low-pass filter. If we let those poles get closer to the unit circle, as they get to the unit circle, the response let's try it again. Or not. Is it hung?
Actually, go to the bottom right. It's in the system.
Oh, there it is. Thanks. Okay, so here as the poles go to the unit circle, get closer and closer, you get more and more spike in the magnitude response that makes sense. So as this distance from this point in the unit circle to the pole gets smaller and smaller, 1 over something small is large, and you get peaks at exactly this frequency, which is roughly pi over 4. You'll notice the roll of the 0 gives you zeros at minus pi and pi, as before.
So the amplitude has to do with how far it is from the unit circle.
That's correct.
Where it actually has those peaks is dependent on
1 over the distance, right? So the pole, again, the poles influence the denominator of the frequency response, and the zeros influence the numerator. So if this distance from the pole to the unit circle is small, that's in the denominator, so 1 over something small becomes very large, and hence you see the peaks here. One other thing, you'll see the phase, oddly enough, even though IR filters don't have linear phase over all frequencies, over the pass bands, you actually see near linear frequency. So what's interesting about certain IR filters is that over the frequencies you care about, the response of the filter is nearly linear. It's almost linear, but it's not linear phase, obviously, over all frequencies. Okay, see you next time.
This is the zero of the origin, basically.
Yeah, the zero of the origin has no effect on the magnitude.